Hello, welcome everybody. It is now a pleasure for me to introduce you to Professor Rafael Herrera Guzman. He's a friend of ours, a colleague from CIMAT Guanajuato, and the subject of his talk is Clifford Monopole equations. Thank you, Rafael.
Okay, so first of all, I would like to thank the organizers for inviting me to give a talk here in this mini meeting. Mini meeting is becoming very popular, kind of meeting. Okay, so the topic of this talk, or the talk is in nature quite ambitious in what I want to present. There are loads of objects I have to introduce and motivate. Now I have an hour and a half, so let's see if any of you survive, or indeed I survive. Okay, so first thing I have to say is this work is a joint work. Like the first 2/3 or 3/4 with with my ex-student Noemi Santana, and the very last part about the multi-equivalent formalism I mentioned in the abstract is work with Alexander Quintero from the Universidad Nacional de Colombia, and the first observation is that this talk is mathematical, is geometry, no physics. It might be related to some names like this one, which are used in physics and theoretical physics, but there will be no physics here. Okay, so the talk will have several parts. So this is the 2/3 I was mentioning, and then this is or the 3/4, and then this is the last bit. Well, let us see. So first of all, the geometrical object that motivated all our geometrical study, has been the notion of Riemannian holonomy. The Riemannian holonomy group. So let me just recall that for a Riemannian manifold, the holonomy group is the group of transformations of the space at a point, orthogonal transformations that are obtained by parallel transporting a frame, an orthonormal frame in that point, parallel transporting it around every possible loop based at that point. That parallel translation of a frame transforms the frame orthogonally, and that gives you all those transformations that you might get will form a group, and that's what is called the holonomy group. This is a point of view of geometry in which Lie groups play a fundamental role. It's, I believe, what motivates then later on the study of G structures and all the possible generalizations of connections and so on, principal bundles and connections. Okay, so there is a classical theorem of Berger and Simons about the holonomy group of an irreducible, non-locally symmetric, simply connected Riemannian manifold. And it says that the holonomy group of such a manifold, and this avoids redundancies, yeah? The holonomy group of such a manifold must be contained in one of these type of groups, classical groups. Well, except for this one, which is exceptional. And I will say some words about this. Somehow this list is a manifestation of that phenomenon of nature, I believe it's a phenomenon of nature, that manifests itself in the form of the existence of only 4 norm division algebras. This is another manifestation of that phenomenon, in the sense that when we write these symbols, we are thinking already of Riemannian metric or an inner product, positive definite inner product. Here we are thinking of unitary matrices, here of quaternionic matrices, here of spin 7, which I'll talk about a little bit, and G2, which is an exceptional Lie group, which are thought to, or are related in one of the manifestations of this phenomenon to octonions. Now, in principle, the algebras found in the theorem are not necessarily defined as complex or quaternionic. They appear as algebraic objects with relations, right? Then we identify that they are the ones that can be defined as complex matrices that fulfill a certain relation, and so on and so forth. Anyway, so given this this phenomenon, when the holonomy group is contained in SON, is what is called a generic holonomy. But when it's contained in these particular subgroups, they acquire well-known names, like the Riemannian manifold would be a Kähler manifold, that has a complex structure which is parallel with respect to the Levi-Civita connection. Furthermore, there are the ones that whose holonomy is contained in this proper subgroup, and that's equivalent to, more or less equivalent to, the canonical bundle being trivial. So, and that translates into scalar curvature being 0. These ones are called quaternion Kähler. This part of the Kähler thing is a bit unfortunate in name because they are not Kähler. But what it intends to say is that there is a globally defined 4 form, in a way playing a very similar role to the 2 form called the Kähler form in this context. The Kähler form is basically putting J inside one of the arguments of the metric. Okay, there is a hyperkähler where the ij and k are global, and therefore we have 3 Kähler forms globally defined. And this one, the exceptional, in 8 dimensions for 8-dimensional manifolds and G2 for 7-dimensional manifolds are defined by what usually, I mean, they are defined by, the geometry is defined by the existence of a global 4 form of a certain type. So, while one thinks of this as complex structures or complex structures playing like quaternions, here we lose that notion. It's defined differently. However, we can see that these ones can be defined by 4 forms and this one by 2 forms. Okay, so it seems that 2 forms, I mean, differential forms play a fundamental role in the geometry of Riemannian manifolds. Okay? Now, the motivation of all the study, of all the results that I'm going to be talking about, is my wish, or our wish, once I introduce my students to this, my wish to characterize Riemannian holonomy in a more uniform way. And that way, the way I wanted to approach it was in a what I call twisted spinorial way. And these terms will become clear, I hope, in a few minutes. Okay, so to contrast, I like to see, myself, I like to see the endomorphisms, the J, the complex structure, the IJK playing as quaternions. But as I mentioned, to define spin 7 holonomy or G2 holonomy, one is usually presented with this kind of thing. And then I have done a bit of digging, and because the references might be very old, I haven't been able to find a good motivation for this. Yeah? But it is a form whose stabilizer is exactly this group inside SO8. Yeah. The motivation, some might argue, is given if you go through the octonions and look at the automorphisms that respect this or that and so on, and you arrive at something like this. But having a detour through octonions, it wasn't something that I really wanted, or I really felt comfortable with, so I wanted to develop a different approach. Okay? Now, why did I have a clue that there will be a different approach to these things? Because Hitchin, in his well, actually, I should start here. Cartan, when he invented the spinners, he invented a notion of pure spinner, which I will recall a little later, to put it in one-to-one correspondence with linear complex structures. So in a way, to try to study complex structures which are endomorphisms via a different kind of object, which are spinners, which live in much bigger spaces. So in a way, he might have been complicating the story, but in a way, I believe it was being simplified or factorized. Hitchin, later on in his thesis, he proved that if there were parallel spinners on a manifold, that manifold had to be Ricci flat. Mackenzie Wang did the study of all those Ricci flat manifolds. Ricci flat is, well, like the ones we have here with zero scalar curvature. So he studied those cases and actually gave a description of such spinners and the forms associated to the geometry. Later on, or much later on, Moroyanu studied the case of pure spin C spinners. I'll show you in a little bit what they are, and he showed that we could have non-Ricci flat Kähler structures associated to them if we just consider spin C instead of spin the spin group. Okay. Now, some of you might recall that the spin C group became very popular when Edward Witten introduced the Seiberg-Witten equations to study for manifold topology, which in some way you will see are related to what I'm proposing in this talk. Okay, so but it is this part in which we can have non-Ricci flat that spurred me into thinking about using twisted spinorial geometry to deal with this case, and this case. Okay? Okay, so all this is just a story. I'm going to give a bit more elements, a bit more substance to all these claims, hopefully very soon. So we achieved this by studying spinners. So here I'm introducing symbols that I'm going to explain in a little bit. Twisted spinners, because this is a spin representation, and I am tensoring with another representation. And those types of representations are spin representations of another group, of an auxiliary group. Okay? So we succeeded in finding spinners whose stabilizer is exactly this thing, which therefore will give us parallel spinners on the manifold, according to a connection on an auxiliary bundle that we need. In other words, what we are trying to do to build this twisted geometry is unfold the geometry of the manifold into two factors, or various factors, and then get this parallelness. Okay? So, please bear with me as I get to that. So the point is to get to the motivation of the Clifford Monopole equations. Once we succeeded in finding these spinners, these very special twisted spinners, which are parallel, if you have one such spinner, the Dirac operator is defined in this way, and if you have a parallel spinner here, this is zero. So this sum will be identically zero. So parallel spinners trivially satisfy what is called the Dirac operator for the bunch of structures that I'm going to introduce. And, well, that wasn't surprising. What was surprising was when I realized that the curvature form of the connection that needs to be introduced in an auxiliary bundle actually satisfies an equation, an identity, with a two-form with values in the endomorphisms of F. And this two-form is naturally, I claim, naturally associated to these spinors we found that we needed to characterize this, the holonomy with. Okay? So, well, we had this equation and suddenly the penny dropped. This is the first equation in the Cyber-Witten equations in 4 dimensions, or pretty much very similar. And this is the second equation, where the curvature of the connection on the U1 principal bundle is equated with the naturally associated two-form to the spinor. Okay? So, well, that's the motivation of the talk. And there is just a little detail here that for this to hold, I need it to be different, and the dimension of the manifold I need to be different from 8, but in dimension n equals 8, there's also an equation, and we will see it. Oh, well, this is the equation. I need to introduce the Riemannian tensor of the manifold acting on such a two-form in a special way, and then this is the full set as I have it right now. Now, the point is, anybody can propose equations and call them whatever you want, okay? And claim that they are important. Well, I'm not trying to do that. I'm trying to say, I found this. So, what I found were these spinors with and connections accompanying them, which are non-trivial solutions of this. What I mean by non-trivial is the solutions to these equations are manifolds that carry special holonomies, and special holonomies have been special, of special interest to theoretical physicists the last 20, 30 years. Okay? Okay, now the point is, as they are similar to Cyber-Witten, immediately people might ask, do you have a moduli space? Can you define invariance? Well, the answer is I do have a moduli space, but I haven't yet got to the invariance part. Okay, we are on it, but it's, if you are familiar with gauge theories, it's not like enchiladas, you know. So in the last part of the talk, I will very tentatively talk about the Atiyah-Jeffrey-Mathai-Quillen formalism. That can be applied to this because that formalism fits in with, Cyber-Witten theory fits into that formalism. So this theory, which I claim is very natural, I didn't make it up. I found it. It's in Riemannian geometry. This formalism also fits very nicely. So there must be a supersymmetric theory somewhere for which this is the topological twist, as I call it. Anyway, one more thing. I must mention that there have been many attempts, well, quite a few attempts by other people to define spin C monopole equations on manifolds. This is quite different from what other people have done. And these have solutions which are natural. Okay, so here I go, and hopefully you will cope with me because there's a lot of algebra here and representations and Lie groups. So I will denote by CLN the Clifford algebra generated by Rn with its inner product, standard inner product, fulfills this relationship. The generators, let's think about it that way. I think in coordinates, in local basis. The Clifford product of two vectors is given by the wedge product minus the inner product of the two vectors. So it basically is a corrected wedge product. The complexification will be denoted with this C. And there are nice isomorphisms, which I will tell you explicitly how you can get a representative of such isomorphism in a minute, in which this algebra with this structure, multiplicative structure, is isomorphic to the endomorphisms of a big space. You see, is if n is equal to 2k, so k is half the dimension in this case. So c to the 2 to the k. So it's a big space. So there's Clifford algebra. This one is isomorphic to the endomorphisms, and if n is odd, is 2 copies of the same thing. In a way, these 2 copies have to do with 1, 0 vectors and 0, 1 vectors in complex geometry sort of thing. Now, it is this space, this big complex space, the one that we call spinors, space of spinors. So it's exponentially big with respect to n. When n is little, this thing is not very big, but once you pass n equals 9 and 10, the thing blows up. Okay? So basically, because of this isomorphism, we have a representation which we call kappa of the complexified Clifford algebra into the endomorphisms of this complex space. Okay, so that's the spinors. So it's not a magical thing. Spinors is a complex vector space. Now, to make it even more pedestrian, to popularize it, one can consider, one can manufacture the explicit isomorphism. So what do you do? The space of spinors is essentially this. C2 tensor C2 tensor C k times. Okay? So, believe me, if you consider these 2 by 2 matrices, which are related to the, is it Pauli matrices? Yes? They are not the Pauli matrices, but it's the choice of isomorphism I have. If you map the generators, E1, E2 of the vector space generating the Clifford algebra to this Kronecker product of matrices, so it's K matrices in Kronecker product, matrix of 2 by 2, this dimension is going to be 2 to the K by 2 to the K. You get explicit matrices, so you're mapping vectors to add as linear transformations on a very big vector space, okay? In the case of n equal n odd, the last vector has to be mapped in a slightly different way because there are no more spaces to put G1s and G2s. You see G1, G2, and then the next space will be T and G1, G2, and so on. You go shifting, shifting, shifting. The last 2, G1, G2, and if you have an extra one, then everything is T. With an I. Okay? I here. Well, that's explicit. Now, in order to write the matrices I just mentioned, one needs a special basis. So I get this special basis for C2, and it's a unitary basis. And you would say, why didn't you get 1, 0, and 0, 1? Because these ones are essentially, or will turn out to be, weight vectors for the maximal torus of spin 2. Well, when I build these ones as a basis for the space of spinors, they will turn out to be the weight vectors of the standard maximal torus in the spin group. I could tell you a lot about that, but I don't have a lot of time. So, there is what is called Clifford multiplication, and basically Clifford multiplication is nothing but taking vectors and by means of the isomorphism. So you have this IN inside of the Clifford algebra. The Clifford algebra is isomorphic to the endomorphisms of this guy. So send it to act this vector as a matrix on that spinor. It has properties that with respect to the standard Hermitian product that you can put in it is antisymmetric, and it can be extended to the entire exterior algebra. You can multiply by forms. Basically you decompose them and apply this rule and associativity. Okay? Now, here we come to the guy I really wanted to use, is the spin group. Now, please bear with me again. Why would I want to explain yet again what the spin group if nobody really understands or care? I mean, it's like, do you know the spin group? Oh yeah, it's a universal cover of SON, and that's it. Well, no, it can be by means of this, by means of this this recipe. It can be made very explicit. Anyway, the definition is the elements of the spin group is the products of an even number of vectors in Clifford product in Rn of unit 1. Okay? Its Lie algebra is spanned by the products of two different vectors. The spin representation is just a restriction of that big representation of the Clifford algebra to this subset, yeah? And it is in fact a special unitary representation. Therefore, and it's a Lie group, and then we have, by taking derivatives, a representation of the spin algebra, and it can be extended to tensor products using Leibniz, yep, which we are going to use. Okay? Now, it is a for instance. You know the recipe I was telling you about, how you send generators, and how, what basis you should use in some order to actually write down the matrices. So this is just an example of how a matrix by this element of the spin group would look like. Yeah? So it can be made very explicit. Okay, so no longer can anybody challenge you. Write a matrix of the spin group in this representation. Oh yes, I can do it. As opposed to, what? Okay, there it is. Okay, now let's go to the concept of a pure spinor given by Cartan. And it can be defined with isotropic subspaces, but I prefer this definition. Basically, now you know you have this very big space. You can write elements in that very big space. So, an element of that very big space is called pure if for every x in the generating space Rn, there exists a y such that this equation is fulfilled. And you'd say, what's the point? The point is the following. Let me first tell you, there exist such things. And one example is the U111. As this is recycled text, probably I didn't explain it. You remember I wrote a vector U plus and a vector U minus? So U111, written in that way, is basically the element U plus, U plus, U plus. There are K here, K times here. All right? And that spinor actually fulfills this kind of equation. It fulfills it for E1 and E2, E3 and E4, E5 and E6 by the rule that I gave you earlier. Now, why is that? Why has that got anything to do with complex structures? Let us play this game. Call it J of X. Put it in there and pass the I to the other side. The rule is for everything there is another one. So, but look, when you do what I said, rename it and pass the I to the other side, you get this equation. But this is the corresponding Y to this guy. So, but I am calling those J of what was on the left-hand side. So this must be J square of X. So essentially what that is telling you is that this equation, this identity, is creating a complex structure for you on the x's, on the vectors of Rn. Yeah? And as I said, they do exist. That was one of the so many miraculous concepts of Cartan. Now, geometrically, what that means, and I can honestly tell you, I have been surprised by when I talk to colleagues, no spinners, about this interpretation. What this identity means, this one, means that when you hit the spinor, this special spinor, by the tangent space, the space it spans is n-dimensional. And this is the same space but rotated, multiplied by I. Let me put it this way. You see, schematically it's like this. Let's say in space you had a Tm by phi. There is no reason why ITM by phi should not meet transversally or in a subspace. What this identity says is that they actually coincide. So what that means is this when you multiply by I, vectors that live there, complex vectors, because now we are in delta n, which is a complex space, is invariant on their multiplication by I. So what that means is that we have a complex space here, a complex subspace. Yeah? Let's put it this way. In C2, if you take R2, that's not a complex subspace. Yeah? The real part. Right? So this is a case in which these spinors induce the meeting of these two subspaces. So this is the geometrical interpretation of this equation inside of this, which means this is complex, and that complex structure that exists here as a complex subspace is induced into Rn by means of this identification. Yes?
Could you remind me of the definition of that product with the dot?
Is
Something minor.
sorry. This one.
Okay.
In a way, take the vector, like this, take the vector, and take it into a big matrix, and hit this very long column vector.
Oh, okay, okay, thank you.
Yeah? So what I'm trying to stress is that it's not something very implicit or mysterious. Can be made very explicit. Okay? Now, as Cartan defined it, these type of spinors have a particular stabilizer, which is a special unitary group, which from the point of view of holonomy corresponds to a special Kähler or what is called Calabi-Yau manifolds. So it's not capturing non-zero curvature, non-zero scalar curvature. So if we use what is called the spin C group, which is twisting it by a U1 in dividing by the center, which is a copy of Z2, with respect to this group, the stabilizer now is the full UN over 2, the full unitary group. Now, let me tell you. So how do you make this act on the spinors? So you take an element here is an element of spin and a complex number. Can you see what I'm writing? Sometimes I write too small. Yep. You take one of those and you will act on spinors. Let's say in the notation I introduced, cap of G. Well, shall I rewrite everything? Yes? Okay, let me rewrite everything. Okay, you have the spin group there, the spin Z group, and I just want to tell you how it acts, because I didn't write it there. So, this will go to that automorphisms of that big space. So you have classes of two elements. Yeah. Okay. And that goes to this kind of thing. Cap of G acting on phi, and then just multiplying by Z, by the number. That's the way you are enlarging. You are enlarging the group acting on this. And the thing is, the U1 that this guy was missing, well, is given by this U1 we are adding. Now we do have Kähler geometry, and there was pretty much the result of Moroiano about Kähler manifolds. So this is one motivation for the search that we undertook. Okay, so now let me, motivated by spin C, I define this twisted spin group, in which I use not U1 or SP1 as you would expect. I use spins, and that is motivated by the following. However infantile you may think this observation is, by definition, spin 2 is U1, spin 3, which is SO2. The connected double cover of SO2. But anyway, let's put it like this. This is SP1, which I didn't define. It's the quaternionic matrices of that A by A star gives the identity. And well, spin 7, which are the ones that I'm after, is equal to spin 7. Well, that's the most infantile line on this thing. Thing is, this is a complex nature. This is a quaternionic nature. Quaternionic nature. And this is the octonionic nature sort of thing. Yeah? And based on that observation, if we already had the Kähler thing, then I wanted to have the quaternionic Kähler, and the special holonomy one, spin 7, and even G2. Okay, so that's why we define this group in this way, which fits into a exact sequence, and has a and this map is just taking however explicit, let me make it explicit. Spin n is 2 to 1. And now how do you see that? Basically, you use an element here, and you send it to the transformation that uses it this way, or the other way around. It doesn't matter. They have, and with that, what you get from an element that is represented into a very big space, but in principle is something that lives in the Clifford algebra, you are able to manufacture, here is the dot, the Clifford product, or Clifford multiplication. You are able to manufacture a rotation. Again, I could explain this in a greater detail with the little examples and the like, but maybe I won't. I don't have the time. Okay, but anyway, there's this double cover to these groups, and the observation is that under this definition, spin 2n is the classical spin Cn group. The Lie algebra of the group is the sum of the Lie algebras of the two factors. Okay, so you might think that is contrived, but I mean, we had a purpose to define this. Okay, and even more, another definition, once you have that group, you can make it act on the tensor products of the representations of the spin n and the representation of spin r, and even tensor powers of that one. This is what I call, or well, will eventually, if I mention it again, is what I call the tangential part of the manifold, and this is the auxiliary part. Okay, these representations are unitary, and elements of these spaces will be called twisted spinors. Or simply spinor if I forget. Okay? Am I going too far? Is this flashcard show or we're okay? Okay, this notation, which is very tiring. So, essentially, when I introduce the new factor spin r, I'm thinking that I have another factor r to the r, and it generates a Clifford algebra, generates a spin group, and so on. So take a frame of this R, is denoted with Fs. And here is the geometrical part analogous to that one of Cartan's pure spinors. Okay, so first of all, when we take a vector of Rn and hit this guy, we get an injective map. I mean, if you have a phi, a spinor that is non-zero in this very big, complex vector space, when you hit it with a vector, you get a subspace here. When you hit it with a vector, and also with these bivectors, or these elements of the Clifford algebra or the spin algebra corresponding to the auxiliary part, you also get a complex you also get a subspace of this big complex vector space. Now, at this point, I'm not claiming that these are complex vector spaces. I'm just saying they are subspaces of this big one and subspace of this big one. We try to imitate Cartan's definition to fit our purposes, but things didn't work quite so easily. So what we ended up noticing was that that from these two formulas, you can go here to here, and then project to here inside this space, and then go back here. Yeah, because it's injective. Both maps are injective. So is it clear? I do this, I go here, project in this space from here to here, and then here. That's what I'm writing right here. You see, when I have a space, an element in that space, the second line I had in the previous slide, I project it to this one in this fashion using the inner product. Right? Okay? You convinced? I mean, the element, I take inner product with the EJ by phi, which is a generator of this guy, and then I put it there. So this is like the orthogonal projection into this direction, and I sum over all of them. So, and this is the transformation I get. Okay? Yeah. So, what is happening is the following. These bivectors are the generators of the spin algebra. Basically, if I am very lucky, by means of these transformations, I will transfer the Clifford algebra relations that these things fulfill in the Clifford algebra CLR, I will transfer it into the endomorphisms of Rn. Yeah? That is the purpose of well, that was the end result of our search for pure spinors. So, that's the definition, precisely. We will define twisted pure spinors as those ones which will induce a non-trivial representation of CLR0, the even part. I didn't define the even part. The even part is basically those ones made up products of an even number of vectors, right? Let's put it that way. And basically, either I can make up endomorphisms or two forms. So if I wanted to write it as two forms, this is the definition. I take the phi, I take the product with these guys over K and L between 1 and R, as it says here, and I take product with this and real part and so on. So that will be a real two form. In fact, this is redundant because these products are always real. They end up being real. So, but just to emphasize, this is a real two form, alternating two form, and we get by metric duality, we get endomorphisms. So here's the definition. A non-zero spinor is called pure if it satisfies these two equations. And you would say, what? Well, here, what it's telling you is that those endomorphisms that we define by means of squeezing the juice out of the spinor are complex structures, local complex structures, or I mean point-wise complex structures. And this one, I will explain in a minute. Well, this one is the condition, it's similar to this one. It's analogous to this one. X phi equal to I y phi. Somehow it's analogous to that one. Yeah? This one is analogous to this one. But it doesn't read quite the same.
I'm sorry, why is it analogous? It doesn't look exactly, it doesn't look quite obvious.
No, it doesn't look obvious. But please believe me.
Okay, I'll believe you.
And if there is time, I will explain later why there is this 2 here and why it's analogous. Basically, this is in case R equals 2, this is kind of a summary of a bunch of equations that are fulfilled for E1, E2, E3, E4, E5, E6. So somehow it's a summary. But then again, the 2 is also different because U1 is different from every other SOR. I mean, SO2 is different from every other SOR for R greater than or equal to 3. And that kind of permeates many of the calculations.
Sorry, could you remind me what FK and FL are there?
Okay.
Sorry.
So you have an auxiliary real space, and this is generated by by a basis, orthonormal basis. And Fi, Fj, or well, I call them Fk KAL is basically FK wedge FL because the inner product is 0.
Okay.
And then
okay.
I make it act on the
Thank you,
on the
thank you.
corresponding representation. Okay, as I said, I mean, I promised it was going to be a lot of information. So it's not easy to keep up. Okay, so the first condition, what it actually gives you is that the endomorphisms satisfy the relations of SOR as a Lie algebra. The commutators give you the relations of SOR. The second one normalizes the spinor in the sense that when I talk about here, these are brackets, Lie brackets, commutators. When I talk about Clifford relations, as in the spin algebra, is not commutators. Products of matrices directly, they fulfill these identities, which are the identities of the spin algebra. You see, the spin algebra in that sense is finer than the special orthogonal algebra. Yeah? Okay. Because it lives within a bigger algebra, which is the Clifford algebra. So what that means is that, I mean, this was kind of what we were looking for, a suitable spinor that would give me an embedding of the Clifford algebra into endomorphisms. And by the way it is defined, and they exist, that is the point, there is a representation of this into the endomorphisms of Rn with no trivial summands. Okay? And that means that because of the simplicity of this guy, that the Rn must be a number of times the spin representation, or the spin representation of the corresponding rank, the real one, or in the cases of R congruent to 0 mod 4, a sum of the positive one with a certain multiplicity plus the negative one with another multiplicity. Yeah? So, okay. So far, so good. Now we have the Clifford algebra acting on the endomorphism. Well, it's, but everything determined by these very special spinors. Now, as it turns out, this is work, part of work with another student, Gerardo Arismendi. The stabilizers of such things will be groups of this type, yeah, where you have the spinor factor, and these are the centralizers. You will see again another manifestation of that phenomenon, in which, and it comes through because of the Clifford algebras, which obey that phenomenon. Clifford algebras are real, complex, or quaternionic. So you see these 3, 4, 5 mod 8 are quaternionic, 2 and 6 mod 8 are unitary, and 0, 1, and 7 mod 8 are real. Now, how will I globalize this stuff that I have done algebraically? Well, this is a trick. How will you mount such an object on a manifold with special structure group or special holonomy? Well, if the stabilizer is contained in the special holonomy, then it will, well, these stabilizers map to this thing, which is covered by this thing, right? And if I am lucky to be able to have the fundamental group mapped trivially, or to the image of the fundamental group here, that is non-trivial, mapped into the image of this one, this map will lift. Therefore, okay, if I have a reduction group to one such group, I will be able to mount this twisted spinorial setup and spinorial representations, spinor bundles on the manifold. So, okay, so let me put it this way. If I have a manifold where I have been able to set up all this spinorial stuff, found this non-trivial vector that causes a reduction of structure, then I get the special holonomy. If I have the special holonomy, then I have all these representation, blah, 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 and I can mount all the spinorial thing by means of this lift, and then I have the if and only if I made any sense. Anyway, that's the globalizing argument. by means of the stabilizer. Anyway, as I said, all these things exist. So I know you won't have time to take notes, but I feel obliged to present it. An explicit representative of such very special spinors for R equal 3 given 4m dimensional space is given by this. I mean, you define psi j this way, phi j this way. These are the u's of the beginning. The v's are like the u's, but the ones corresponding to the auxiliary part of R to the R. These are the spinors with subindices plus minus 1 and so on and so forth. You take this sum, and that is precisely a pure spinor for rank equals 3, which means for quaternion Kähler geometry. So I have achieved Moroianus result. Okay? And indeed, the two forms that you can squeeze out of this spinor read like the two forms that you see locally defined in or dualizing the local complex structures of a quaternionic geometry. I got stuck. Yeah. Now for R equals 7, we have a similar story. We can write down explicit representative that will reduce the structure group to a copy of spin 7, according to our definition. Okay? So we succeeded in characterizing holonomy with twisted pure spinors. Okay? But more importantly, now I have unfolded the geometry, and this is a case that is really interesting. Was nice to me because these guys, the two forms that I squeezed, if I metric dualize to endomorphism, they satisfy the relations of spin 7. So, and based on them as two forms, if I sum over them like this, in that example, if I sum K, L, 7, 1, phi, to phi, KL, I get the famous full form omega. That one is given in the definition of spin 7. So no longer can anybody tell you, write a matrix of spin 7. Oh, there it is. Yeah, you can write, or a two form, and write where does it come from, the full form. This kind of summarizes all the information that is in the Lie algebra. Yeah? Well, one can do it now. An observation. I cannot only write naturally one representative, I can write many representatives. Because this spinor, I can take an orbit under the spinor subgroup of the twisted spin group and generate many more spinors. So that will give me the same geometry, the same structure. Anyway. Okay. Okay, globalizing. Well, this is very tiring. How do you globalize? This is what I was hinting at. You have an oriented n-dimensional Riemannian manifold. You have the principal bundle of orthonormal frames. Take an R greater than or equal to, a spin R and a structure on it, consists of an auxiliary bundle. And either of these two things. You have the auxiliary bundle, and I mean this has group SON and SOR. And then what you had point-wise, SON, SOR covered by a spin R N group, by this twisted spin group, you have to have it global in terms of principal bundles. Either that or the manifold is spin itself. Yeah? Because that happens with spin 7 manifolds. Okay? Once you have this, or this together with this, you can glue or associate vector bundles, things like the standard one or the spinorial ones. I mean, once you have such a thing, so I'll write it explicitly. How much time do I have? Well, let's see if I can get to it. Once you have this guy with this structure group, you can make but take the tensor product, the direct product with these, and make a quotient by the representation, by the corresponding representation. So I quotient out by the structure group, and I end up with a vector bundle. That's what I mean, what you achieve. And abusing the notation, you will see that I will denote these by the same symbol, if you forgive me. And why do I do that? Because the font in these slides is very big, and otherwise things just get longer. Okay. Okay. So in terms of the globalizing, you assume that the auxiliary bundle has a connection. You take the Levi-Civita connection on M. You induce a covariant derivative on this twisted spinor bundle in the usual way, using these forms. You have the 1/2 because we are lifting. You have the kappas here and so on, and that's a connection on space of sections of this. Okay? Then we can talk about what it means to be parallel for one of these guys, and this is a sample calculation of the many calculations that one can do, because now I'm heading towards what? I'm heading towards the, or trying to justify lightly the identity of curvatures. If you have, so if you have a parallel spinor where you have this auxiliary bundle and auxiliary connection theta, take local frames, they satisfy these derivatives, covariant derivatives, and then you take derivatives of the two forms that we define. If one takes covariant derivatives of those two forms, one has taken derivative of this evaluation of the two form, you get this term plus the covariant derivatives that are here are inputted here. Okay? You get this identity. On the other hand, you take the definition using the spinor. You see, I'm changing here using the spinor. And the covariant derivative is compatible with the inner product, compatible with the Clifford product, compatible with everything. It opens up, and then you end up with this identity. That the endomorphisms of the two forms, the bundle of two forms that you have defined by means of the parallel spinor, is a parallel bundle. If you take a derivative of it, it stays within the same set of combinations. You see? So what we're saying is the structure that we have is parallel with respect to the Levi-Civita connection. Okay? Now, after many more calculations, taking more derivatives and taking things to one side, the other, using Bianchi and so on and so forth, one gets to this identity. Yeah? And here's when it becomes, is that correct? No, even before that. But it becomes relevant that n is different from 8. So what it is telling you is that by means of the existence of a special spinor, it means the auxiliary vector bundle that looked arbitrary, the auxiliary connection on that bundle that looked arbitrary, when you have a parallel spinor, it brings them together into the geometry of the manifold. Now, to simplify things, if one made the assumption, but this can be actually deduced in n different from 8. If one made the assumption that the manifold is Einstein, that means the Ricci tensor is a multiple of the identity tensor, one gets to the following identity. Okay? And that is essentially what I meant was what I eventually thought, but that's the second equation of Seiberg-Witten's equation, but in a more general context. Okay? So you must be dizzy by now. Don't worry. I won't stop. Okay? Okay, so one thing. The name monopole. Why monopole? In theoretical physics, they called an instanton a connection on a principal bundle that satisfies a certain equation, self-duality as they call it. But when they have a pair of an object usually fermionic, as I call it. And a connection, that's what they call a monopole. It's kind of a traditional name. Okay? Now, not only because it is a spinor and a connection, but because of the similarity, which I will elaborate a little more in a second, that's why I call it Clifford Monopole equations. Why? Because the idea that is behind it is the transfer of a Clifford structure into the manifold. That's how I found solutions to these equations. Okay? And I think that's a catchy name. When everybody knows Clifford algebra, so it's catchy. Okay. So again, I remind you that the Dirac operator in this context, don't worry, I won't do anything silly. There should be a theta here, yeah? Because the covariant derivative applied to the spinor involves the auxiliary part with the theta. Okay, so that's the Dirac operator. So the Clifford Monopole equations can be written like this. Here is an extra layer of generality in which the curvature tensor of the Riemannian manifold sends two forms into two forms. So it's a special, I mean, I have to write it in coordinates to explain it, but it's kind of an action on the two form associated to the spinor. How do you construct that two form? These are the two forms local for each k and l. Now, if you take the sum of all of them, that is a global object. Yeah? That is globally defined. Although it is written in a local frame, this is globally defined. The same as a curvature form of the curvature form of the auxiliary bundle. Okay, they satisfy that equation. Okay, so let me elaborate a little bit. Okay, so when you have a two-n-dimensional, now I'm going to particularize, you have a two-n-dimensional Kähler-Einstein manifold with a J which is parallel. You have, because I said it's Einstein, you have constant scalar curvature. You have a canonical spin-C structure given by the canonical bundle, which inherits a connection from the Levi-Civita connection, theta. You can write this spinor, very explicit, which is pure in the sense that we stipulated. And the endomorphism is a standard J of the -1, 0, -1, 0 in this local frame. And the curvature form of the canonical connection satisfies this very identity. If I normalize the spinor, this one, in this fashion, what I have is a solution to the Clifford Monopole equations. Okay? Now, if I set n equals 2, so that'll be a four-dimensional Kähler-Einstein manifold, and I rewrite the equations, I mean, is the argument I had before. Yeah, I have solutions. Now, if I decompose, because I'm in dimension 4, so the delta n is delta 4, and it has a positive and a negative part. I never told you how the positive and negative spinors are, but anyway, has a positive and a negative. Let's say delta 4 splits into this and this, which is the +1 eigenspace and the -1 eigenspace of an involution, which is Clifford multiplication by the volume form. Okay, so you have positive and negative, and you have Dirac. Sorry. You have Dirac operator on the positive part of the spinor, Dirac operator on the negative part of the spinor equal to 0. Those two parts are orthogonal. So you have two equations, the one for the plus, the one for the minus. Similarly, if you take self-dual forms and anti-self-dual forms, here the plus part will give you a self-dual form, the minus part will give you an anti-self-dual form. It's just the algebra of spinors in this dimension. And so you get two sets of equations. But then the Schrödinger-Lignerovich formula, which I'm not going to write, tells you that if you have a solution for one of them, you don't have a solution for the other one. Yeah? And so basically, you end up with exactly these are the Seiberg-Witten equations under this hypothesis. So my claim is the Seiberg-Witten equations are also a very geometrical set of equations. They don't just come from theoretical physics arguments. They come from geometry. Another observation is, if you remember, Seiberg-Witten theory is most successful when you have Kähler surfaces, yeah, or four manifolds which are Kähler. And so all these kind of ties in. I could make other arguments, but this is kind of a simple way of seeing how the Seiberg-Witten equations are a particular case of Clifford Monopole equations, which have natural solutions, which are the special holonomy geometries of Riemannian geometry. Okay, just to round up this thing. Okay, I still have time. Are you still alive? More or less? Yes. Okay, the quaternion Kähler story. You have 4-dimensional manifold. Yeah, no. The problem is not the time. The problem is if anybody is still breathing. You see? So you have a rank 3 subbundle generated by the IJK. This is the F that I was writing before, but in quaternionic geometry usually is denoted by a V or a Q, rank 3 subbundle of the IJ and K. The theta connection is the one induced by the Riemannian geometry of M on this space of endomorphisms, which is parallel. And the phi 0 I told you earlier, we can glue it up. It satisfies that the endomorphisms of associated to it are the IJK. Because this is recycled text, I didn't put IJK, I put JKL in the general notation. And it satisfies this equation. These were equations known by Ishihara. When they first studied quaternionic geometry, they were trying to prove that they were Einstein. So in the first proof, it's a lot of tensor calculus. They come to this identity, which is again the second equation or is analogous to the second equation of Seiberg-Witten. To satisfy the two equations, you have to normalize slightly, and that's it. In dimension 8, which I avoided at some point, the story goes the same, but you have that the form doesn't quite satisfy the -1/4 this guy, the curvature has to be acting on it. Now, reasons for that is because dimension 8 is a very special dimension, as well as dimension 4. And that's it. So that's why this is the general form of equations. Okay. Now I'm going to tread very carefully in the last part of the talk, because I'm not an expert on this, but we thought, how do we push this? Where do we push this first, in order to show that it has some value? So, as I was talking with Alexander Quintero, who's a mathematical physicist who knows lots of stuff, and I could shamelessly ask him all my stupid questions, and he could kindly and obligingly answer all of my stupid questions. So we got collaborating with all his knowledge. Okay, so where am I going with this? I'm going towards trying to play the moduli space story in some way. So suppose M is compact without boundary. Now, well, let's do it a little bit in general. No, sorry. Before anything else, I want to explain the very little I understand of the Mathew-equivalent formalism. So take a compact manifold without boundary, a vector bundle on it whose rank is the same as the dimension of M. The Euler number of this thing is the Euler class of it evaluated on the fundamental cycle. Okay? Now, if E were the tangent bundle of M, we know these results as the index theorem, or and this one as the Gauss-Bonnet theorem, right? You agree? Well, in any event, for E, What it means is you have a section, you can have a section of the bundle and you compute its Euler characteristic based on the multiplicities of its zeros of the vector field. That's one way of seeing things. Another way is like Chern-Weil theory. You find a connection and you construct the Euler class as the Pfaffian using that connection. And so you construct a characteristic class and evaluate over M, integrate over M. So this is like vector field, and this is a representative using a connection, Chern-Weil theory. Correct? What Mathew and Quillen did was to give other representatives of this of the Euler class to evaluate this thing. Representatives that both depended on a section and on a connection. And the argument went like, if the section you multiply it by a lambda and you let lambda go to infinity, you get this result, and if you let it go to 0, you get this result, or something like that. And that is the formula, well, that is the rigorous thing that Atiyah and Jeffrey took to infinite dimensions, and is what is called the Mathew-Quillen formalism. Why? Because the integrals involved are not well defined, and all sorts of problems in infinite dimensions, besides defining cohomology classes. Okay? So, that is a Mathew-Quillen formalism. Well, that's the Mathew-Quillen thing, and then the Atiyah, Jeffrey, Mathew-Quillen formalism. So what do we want to do? Do it in, and what they have done for other modular spaces of instantons and of monopoles and so on, is take the following. Take the configuration space. For us, in the formalism, because we are applying this formally, is the connections theta and the spinors phi. At this point, I'm no longer supposing things are pure or parallel or whatever. Just have this configuration space. We have the gauge group. The gauge group in this occasion, where is the connection? The connection is in the auxiliary bundle. So, it's the gauge transformations of the auxiliary bundle. That is the gauge group. We have a smooth, large moduli space of irreducible configurations, which is, that's the assumption, is a quotient of the A by the G. Now, I'm being very careless in details. I'm not talking about centers or effective actions or something like that, but the story more or less goes like this, okay? Then we have an infinite dimensional principal bundle. Here is the base. I mean, here is the base, this is the principal bundle, and this is the fiber, the gauge group. The gauge group is represented in this space. And why this space? Because this is where theta lives, the curvature form. And this is where the spinor that satisfies the Dirac equation lives. Okay? So the associated infinite dimensional vector bundle, the E of the previous slide, would be this one. You are associating by this type of construction to A, to the principal bundle, you are substituting the fiber, the group fiber, by this vectorial vector space fiber. Okay? So the idea of the formalism is try to compute the Euler characteristic of this thing. The formula is the integral of a path integral of the exponential of an action, and that action reads like this long thing of 6 summands, where all these things are variables that appear because of necessity of the variables of the space and the tangent variables and so on and so forth. Okay? Now, what we have done so far, which already hints, because of naturality, but why we can, the main test is, if you manage to rewrite J in terms of your data, then you are going the right way to create your topological field theory. So this is what this slide shows. The calculations of those summands of the J are explicitly these guys. Yep. The idea, in the end, is the following. The sections, you remember I told you about this story. The zeros of a section or the connection, the evaluation of the connection. So here, the idea, and then to compute invariance, the idea is we have a section identified as a geoequivariant map from the principal bundle to the vector space. Yeah? We have a canonical section in a way. These are the Clifford Monopole equations. Yeah? That gives us a section of this bundle. So, they are, and the G-equivariance means that the Clifford Monopole equations are invariant under the action of the gauge group. They are gauge invariant, which is the first thing you have to check in a gauge theory to create a moduli space. Then we have this section. The zero set of this section is the moduli space of Clifford monopoles. Okay? Now, two things. In terms of the formalism, what we need to do is localize the integral to this zero set of the sections, like in Poincaré-Hopf. That's the formalism. Okay? Now, the plus point is that we do know that we have a moduli space under reasonable curvature conditions. And that is given again via Schrödinger-Lignerovic's formula for negative spinors. And in particular, this curvature condition is easily shown to be true in quaternion Kähler manifolds. So we have moduli spaces of these things for quaternion Kähler manifolds. Now, I'm not telling you any more details about what is the expected dimension of that moduli space, because those are characteristic numbers which are very complex and so on. Moral of the story, we found, trying to characterize special holonomy, we found a special set of equations that can have moduli, will probably give a topological field theory for various special geometries, probably not in general. So there is an open field of research. I mean, well, field is an exaggeration. An open something. An open set of questions in which we can work. Pardon?
Open industry.
Industry sounds a little bit like I'm just kind of. It's cooking things up that are artificial. I mean, my point is that these are very natural things, and I believe a lot of hard geometrical questions like, hard geometrical questions like the classification of 8 manifolds with spin 7 holonomy, the classification might be tackled, at least partially, using the moduli spaces of these things. Okay? If you know anything about those manifolds, you know that there is nothing in terms of classification, next to nothing. So we are optimistic, and well, anybody is welcome to join the club. That's it.
Are there any questions? Yes.
Why? Yes. Why do you need to twist the representation of the Clifford algebras with this M? Why is it necessary?
This factor?
Yeah.
Well, precisely. I mean, there is prior geometrical knowledge, representation theory, in which, when I was looking for the partially pure spin, not partially, that's a different story. By the pure spinors, which are parallel, I knew how these representations decomposed under the holonomic group I was examining, SPN, SP1. I know exactly how they decompose. And if I was looking for a trivial element there in the representation, if the decomposition contained no trivial representation, sub-representation, I wasn't going to find my spinor. I had to go to a certain power. Yeah, so this is a level of generality that is needed to find the special spinors I needed for holonomy. However, once we found that, this parameter could play a role, we just left it there. Does that make sense? It was a necessity to find the spinors I wanted.
Thanks.
Any other question? Well, we thank Rafael.
Thank you.
We'll resume. We have a 30-minute break and we'll be back at 4:30.
And by the way, I think there are some people here who haven't registered yet. So I think so. We have your